Ultrapure water does not lose purity in the pipe. It loses it at the interruptions, weld beads, dead legs, and a cleanroom class. Most specifications get wrong. This is where high purity piping actually fails. This is an Axion ultrapure water treatment train. Reverse osmosis, continuous electrodeionization, final polishing, running at the theoretical limit of purity, 18.2 megohm centimeter resistivity, total organic carbon in parts per trillion. Generating water this pure is a solved problem. Holding on to it is not. The moment that water leaves this skid, the problem stops being water chemistry and becomes network geometry. Purity now has to survive thousands of feet of distribution piping before it ever reaches a wafer. Downstream of that skid, the delivery system looks trivial, just straight plastic pipe. That appearance is the most expensive misunderstanding in fab infrastructure. Trace a contamination event back to its origin and you will almost never find it on a straight run of pipe wall. You find it at an interruption. Every interruption disturbs laminar flow and creates a swirling eddy, and those turbulent zones are traps where particulates settle and biofilm establishes. In an ultra-pure water system, a geometric change is never a neutral detail. It is an active liability. Eliminating those liabilities starts with the pipe material. The industry routinely conflates two different qualifications: chemical resistance and high purity. They are not the same specification. PFA is engineered for aggressive chemical delivery, hydrofluoric and sulfuric acid. That is a corrosion problem. An ultrapure water distribution loop is a contamination problem, and it is typically built on PVDF piping, specifically virgin unpigmented Solif 1000 resin. Its ultra-low metal leach-out is not produced by chemical cleaning after installation. It is an intrinsic property of the raw polymer. Purity also depends on the inner surface. A rough bore snags contaminants and gives biofilm somewhere to anchor, while a bore engineered to a roughness average of 0.15 microns or less lets particles glide past unimpeded. Surface roughness is a purity specification, not a finish detail. Holding that profile requires extreme environmental control during manufacturing, and this is where most specifications quietly fail. Suppliers claim cleanroom grade, but precision matters more than the phrase. Asahi Purad UHP PVDF pipe is extruded on dedicated equipment inside an ISO 5 environment. The ISO 6 Class 1000 cleanroom is a separate facility used for custom spool fabrication, welding, and bagging. Both facts are real. They describe different steps in different environments. Accepting cleanroom grade without verifying which ISO class applies to which step introduces hidden contamination risk into the fab's baseline infrastructure. Even perfect pipe has to be cut, and that creates the first major geometric interruption, the joint. Every one of those connections is a specification decision. Join with the conventional butt weld, and molten polymer pushes inward, forming an internal bead that acts as a microscopic dam. Laminar flow breaks across it, eddies behind it, and a permanent stagnation zone forms where bacteria accumulate. One weld bead cancels the value of all the surface smoothness upstream of it. The engineered answer is beadless infrared fusion, also called IR fusion welding, a joining method that leaves no internal weld bead at all. Non-contact infrared heating brings both pipe ends to fusion temperature without touching them, and controlled cooling pressure joins them with a flush internal bore. No protrusion, no ledge, no stagnation zone. The flow path stays continuous through the joint. In high purity service, a weld is not merely a mechanical connection. It is either a purity feature or a purity defect. Then comes the hardest geometry in the loop, branching water off the main header to feed a wet process tool. This creates the dead leg problem. A dead leg is stagnant water trapped between a flowing main header and a closed isolation valve. Ultrapure water begins degrading almost immediately once it goes still. Total organic carbon climbs, biofilm establishes, and that stagnant pocket sits directly upstream of a wafer process tool. This Asahi Purad piping diagram maps the components engineered to eliminate that vulnerability.
The T343-0 dead leg valve positions its sealing weir flush against the inner diameter of the main run, so fluid stays in the moving header until the valve is actuated. The valve body integrates into the T with no space for water to sit idle. 0 dead leg is a geometry decision made at specification, not an accessory added afterward. Now expand that across an entire fab's fluid infrastructure. The output of an entire ultra-pure water generation plant is at the mercy of the geometry downstream of it. Advanced facilities cannot buy high-purity pipe as a bulk commodity. They have to engineer an integrated ecosystem, virgin Solef, 1000 resin, flush beadless joints, and 0 dead leg branch architecture working in strict unison. A compromised specification at one joint contaminates the fluid path permanently, which raises the actual commercial problem: how that infrastructure gets specified in the first place. Liberty CES does not perform installation labor on the fab floor, since the mechanical contractor owns the physical build. Liberty CES owns the specification layer, interpreting the process requirements, selecting the Asahi Purod architecture that matches the fluid dynamics, and verifying ISO-rated manufacturing origins before a component is ordered. That is the layer where contamination risk is eliminated or quietly designed in. In semiconductor infrastructure, you are not paying for pipe. You are paying an expert to eliminate the interruptions. So here is the question worth asking about your own distribution loop. Does anyone actually know which ISO class made your pipe?